you should briefly pause the video and read this problem. In your reading, I'm hopeful that you noticed a couple of interesting points about this question. First, that we are going to write a piecewise function where distance is a function of time. Secondly, you'll notice that each part of the triathlon is done steadily at the same speed the entire time. This would be an incredibly difficult question and a totally different learning experience if the participant was not steadily swimming, cycling, and running at the speeds that were suggested. Lastly, while they gave us the distances for each section of the person's participation, what they did not give us was the amount of time it would take each person. And that's where distance equals rate times time comes in. Telling us the distance that the person had to travel and telling us the rate at which the person was traveling was a backhanded secretive way of setting up the domain of this piecewise function. Each section of the person's participation requires a different amount of time. Obviously, the distances are very different. Yeah, the speeds vary also, but the distances are very different, which to me suggests that we need to figure out the distances for each and the time for each, because they're also very different. So, looking at the first part of the ride, the first part of the triathlon. The first part of the triathlon is a 2.4 mile swim, and the person completes it at a steady rate of 2 miles an hour. Using distance equals rate times time, we see that it will take the person approximately 1.2 hours to finish the first section of the race. This T is the T that we're going to use down in our piecewise, because that's the time it's going to take the person to finish. So the first section of our domain is going to go from 0 to 1.2. The second section is the person participating in the bike race. Same exact logic. We want to determine how long it's going to take for them to finish the bike race. Dividing 112 by 20 gives us this part that it'll take the person approximately 5.6 hours to finish. But that 5.6 hours doesn't start until the swimming section is done. So I can't just say 0 to 5.6. I'm going to pick up my domain at 1.2, and I'm going to continue that domain. We don't want the equal to here. And I'm going to continue that domain until that 5.6 hour section is finished. That section will be finished after 6.8 total hours. And for the last section, we have to take a little bit of liberties. 26.2 equals 9t. That gives us that the amount of time it will take is approximately 2.91 hours. So from that 6.8, which is going to be the beginning of the last section of the race, up to and including 6.8 plus 2.91, which means our race is going to end after about 9 71/100 hours. After we've identified each section of the domain and split the piecewise into the 3 separate pieces, one piece for swimming, one piece for cycling, and one piece for running, we then can start to build the function. Over here, we want to make sure that our function actually finishes at the time we suggested. We are giving the individual 1.2 hours to do the swimming section. We know that the person is going 2 miles an hour, so let's make them go 2 miles an hour. We'll do the same thing for the biking section. In the biking section or the cycling section, they're going to cycle at a rate of 20 miles per hour. But that's after already having finished the swimming portion of the race. So having finished the swimming portion of the race, plus 20, and that 20 is going to be per hour. But that 20 per hour doesn't start until the swimming section is finished. Thinking about our gym membership from the last example, the section where we had to pay $8 extra for each visit, that didn't happen until the first block was done. Same thing here. That 20 is not going to happen until the first set of time is done. Once that first set of time is done, then we move on to the next part. Then we move on to the next part. In the next part, we have the biking section and the swimming section are both finished. So we're going to have the 2.4 for the swimming section and the 112 for the biking section already done. Once those are done, I look for my rate. My rate for running was 9 miles an hour, but that 9 miles an hour will not start until the swimming and the cycling are both done. Looking back on this in totality, it's actually a little bit easier to see the pattern that gets followed. So in front of the independent variable in each one of the lines is the speed at which the person is traveling. Following that is the independent variable, the amount of time they need to do it for. In these two cases, we subtract time from them because those parts of the race are already finished. How do we compensate for that? We compensate for that by including the finished part of the race elsewhere in that part of the piecewise. So the swimming section is simply done at 2 miles an hour. The cycling section, the 2.4 miles of swimming is already done, plus the 20 miles an hour for the extra amount of time it is to get the cycling done. Then the running is happening at 9 miles an hour only after the 6.8th hour and the first two parts of the race are finished. You can see how the logic in this question follows the logic of the gym membership question. Yeah, it's a little bit different because it's got the independent variable in every level and it doesn't have a horizontal section to it where you're paying a flat rate. But the idea that that part of the next part of the function does not pick up until the last part finishes, that's where we're going to get that nice consistency of the graph where all of the pieces connect. Looking at the graphical representation of the function that we just created, you'll see how the three pieces connect at those key dividing points in the domain. So here's our connection at 1.2, and here's our connection at 6.8. Now, depending upon which function you come in at, you may have part of it that's undefined. That's not relevant to our conversation. We know that at that moment we are switching from swimming to biking or biking to swim or whatever the transformation is. So we're not so concerned that there might be an undefined end. We are still getting them to join thanks to the fact that there are some equal to's in each of these parts. You'll notice very clearly that we have the least steep part here, which is what we anticipated. We have the steepest section in the middle where the biking is happening. And then we have the middle steepness for the running section at the end. That speed is in between the swimming and the biking. You'll notice that this entire thing is happening in the first quadrant. It is only interesting domain-wise that we are limiting this to above 0. It's the same logic that we ran into with the gym membership. We don't want to extend below 0. We could imagine that he does this for the participant does this for 0 a number of hours. They decide not to do it. We want there to be a point at 0, 0. But as soon as they jump in the water and start swimming, we want to be able to follow those consistent speeds the whole way. The defining word in the question that we identified at the beginning, one of the key words in the question was steadily. We wanted this to happen steadily. It's okay that the individual pieces are steady, but the entire thing is not steady. As you move through other algebra courses and you move through more advanced math, you'll start to see how you can connect them all together and get like an average steepness. But for right now, we're okay that these three pieces have 3 distinct steepnesses. The range is whatever number of miles they need to finish to complete the race. And lastly, you'll notice over here that this doesn't look exactly like what we had on the previous screen. Similar to what we did with the gym membership example, you can simplify those two parts of the formula. And yeah, you can. And that's what I did here for the sake of typing so that you could see it a little bit easier and see what that looks like. But there's no necessity to do that. You could have left them separated and really drive home the fact that this piece, the biking piece, can't happen until swimming happens, and that running can't happen until both of those other ones happen. But this is the consequences of doing this in a piecewise format, where maybe you want to simplify to make it a little bit easier to look at. And you certainly, in an example like this, do not want to leave off the previous sections. We were able to reason our way through that with the gym membership, but we don't want to leave off the 2.4 miles that we already did when we do the biking section. And we don't want to leave off the 2.4 and the 112 that we already did when we did the running section. We want to make sure that those parts are there. So looking at a linear piecewise function like this that tells a story, we want the lines to connect. Obviously, we want individual pieces to be steady, but we certainly want to make sure we're telling the right story. We're limiting our domain to the first quadrant. We're limiting our range to the first quadrant. We're staying inside of that space where the functions can actually exist. And we're making sure that we're very careful about how we type it, or in a calculator or in an online tool. We're very careful about the way that we type it so that we actually get that clear delineation between the sections, and you can see the changes, and then you can very clearly see the starting point and the end point.